Okay, with this example, we are supposed to find values of c and d, which make the function f of x, which is defined via this formula here. We need to find c and d, which make the function f continuous everywhere. All right, well, what we notice is that our recipe for the function changes sign on either side of the values 1 and 3. And because when x is strictly less than 1, f is described by a polynomial function. When x is strictly between 1 and 3, f is defined by a polynomial function. And when x is bigger than 3, f is defined by a polynomial function. Regardless of what c and d are, we can say that f is continuous on each of those intervals, just because polynomial functions are continuous. So let's write that down. All right, so solution. So the first thing is that we'll note is that as polynomials are continuous everywhere, f is continuous on these intervals here, well, minus infinity to 1 open, all right? For x less than 1, f is described by this polynomial function, and the polynomial function is necessarily going to be continuous for x less than 1. So regardless of what c and d are, this function is going to be continuous for x less than 1. So f is continuous on minus infinity 1. That's an open bracket. Also, so I'm going to write a union on the open interval 1. Just erase that. So 1, 3, open, because if x is strictly between 1 and 3, f of x is going to look like x cubed, and x cubed is again a polynomial function which is continuous. So f is going to be continuous on the open interval 1, 3, and also on the open interval 3 to infinity, again for x bigger than 3. And remember, if x is bigger than 3, x may as well be a very far ways from 3 when it comes to talking about continuity. And so for x bigger than 3, f of x equal to 2dx plus c is going to be continuous at such an x. So on the interval 3 infinity, this function is in fact going to look like 2dx plus c. Again, it's a polynomial, and so again it's going to be continuous regardless of what d and c are. All right, so the places where f might fail to be continuous are at these points 1 and 3, which are those places where the recipe for our function changes. All right, so what we're trying to do then is find c and d really, which will make f continuous at 1 and 3. So that's really our problem. Okay, so let's write that down. Okay, so we must find c and d such that f is continuous at x equal to 1 and x equal to 3. We're getting continuity, as we said above, everywhere else for free. Okay, so let's see, what do we need to say? Well, what does it mean for f to be continuous at 1, and what does it mean to say that f is continuous at 3? So first we'll deal with continuity at 1. F, maybe I'll make this blue. F is continuous at x equal to 1. Well, what does it mean to say that f is continuous at 1? We just go to our definition of continuity at x equal to 1, and it says that f is continuous at x equal to 1 if and only if, so if and only if the limit of f of x as x tends to 1 is f at 1. That's what it means to say that f is continuous at x equal to 1. Now, because our definition of f is changing on either side of 1, remember it changes, looks like this to the left of 1, and it looks like this to the right of 1, it makes sense to look at that limit in terms of left and right hand limits. Okay, so back down. We'll say then that this is true if and only if, so this limit of f of x as x tends to 1 is f at 1 if and only if, oh, and we should add something. What is f at 1? Let's go up. Again, what is f at 1? Well, looking at our recipe for f, when x is equal to 1, x is certainly greater than or equal to 1, so we use this formula for f. F at 1 is equal to, f at 1 is equal to 1 cubed, which is 1. All right. So this is equal to 1. All right, and this limit is 1 if and only if the corresponding left-hand limit at 1 is 1, and corresponding right-hand limit of f at 1 is also 1. All right. So let's take a look and see what those left and right hand limits actually are. We'll check and see what these left and right hand limits actually are, and we'll try to make C and D, we'll try to ensure that C and D are chosen so that both are 1. Okay, so this is true then. So let's go off here then, I guess. So looking first at this left-hand limit, the limit as x tends to 1 from the left of f of x is equal to, well, when I'm taking the limit as x tends to 1 from the left, remember, this means that, first of all, x is tending to 1, so x is approaching 1, and it also means that x is less than 1. So this means that for all x's that we're considering, x is going to be less than 1, so we need to ask ourselves, what does f of x look like when x is less than 1? And if we go up here, we see that when x is less than 1, f of x looks like cx cubed. So when x is less than 1, f of x looks like cx cubed minus dx. All right, so when we calculate this limit, we'll use cx cubed minus dx for our formula for f. All right. So this is equal to the limit as x tends to 1 from the left of, as we said, c x cubed minus dx. And if you calculate this limit at 1, what do you get? Well, we can just replace the x in this formula by 1, and we'll get c times 1 cubed, which is c, and minus d times 1, which is d. All right, so what are we going to want? We're going to want this left-hand limit, which equals c minus d, to equal 1, if f is going to be continuous at 1. We also are going to need the right-hand limit to be 1, so let's check and see if we've got that. All right, so let's take a peek at this right-hand limit. All right, so the right-hand limit of f of x as x tends to 1 is equal to, well, when I'm now taking this right-hand limit as x tends to 1, all x's that we're considering are going to be bigger than 1. So let's go up to the top to see what f of x looks like when x is bigger than 1. All right, so let's see. Here it is. All right, well, when x is bigger than 1, f of x just looks like x cubed, so we'll use x cubed in our formula for f when calculating this right-hand limit. Okay, so this is equal to the limit as x tends to 1 from the right of x cubed. To calculate this, we can just replace x by 1. We get 1 cubed, which is 1. And if we look, what did we want? For f to be continuous, at 1, we wanted this right-hand limit to be 1. And in fact, that's what we've got. So we get this for free. So let's just put a big check mark here. But, as we said before, we don't necessarily have that this left-hand limit is 1. The left-hand limit is always going to be c minus d. We need the left-hand limit to be 1. It equals c minus d. So what we need is we need c minus d to equal 1. All right, so that's what we need for f to be continuous at 1. So let's write that down. Okay, so for f to be continuous at x equal to 1, we need 1 to equal, as we said, that left-hand limit of f of x, but that left-hand limit is actually c minus d, so we need 1 to equal c minus d. Okay, so this is what we need. We need 1 to equal c minus d. All right, so that is, we need c minus d to equal 1. All right. So the first condition that we're going to need for f to be continuous at 1 is c minus d to equal 1. And if we go up, we saw that what we were looking for was we needed to find c and d so that f was continuous at 1. For f to be continuous at 1, we have this condition that c minus d is 1. But we also need f to be continuous at 3. And choosing c and d so that f is continuous at 3 will give us another equation in C and D. So let's take a look at this part here. We want to find C and D now such that f is continuous at 3. All right. Okay. So, let's pick another color here. Green, say. So also, f is continuous at x equal to 3 if and only if, well, the condition for when f is continuous at 3 is satisfied. So if and only if then the limit of f of x as x tends to 3 is equal to f of 3. And again, the recipe for f changes on either side of 3, so it makes sense for us to write this in terms of left and right hand limits. So this is true if and only if the, oh, and we should say, what is f at 3? Let's go up and check. What is f at 3? So, so if and only if, let me see. Okay, so up we go. At x equal to 3, f of x is given by this formula here. So when x is 3, f of x is 2d times 3, which is to say 6d plus c. So f at 3 is 6d plus c. Let's write that down. There we go. So equal to 6d plus c. So I think I have to write that down here. 6d plus c, and this is true if and only if the corresponding left and right hand limits are also 6d plus c. So if and only if, see, the left hand limit at 3 is 6d plus c, and the right hand limit at 3 is also 6d plus c. Alright, so f is going to be continuous at 3 if and only if the left and right hand limits of f at 3 are both equal to 6d plus c. So let's take a look. So first of all, what about this left hand limit? So the left hand limit at 3 of f of x, that's equal to the limit of f of x, so x tends to 3 from the left of, well, when we take this left hand limit at 3, all x's that we care about are going to be less than 3. So let's see what f of x looks like for x less than 3. And if you go up to the top, I don't think I'm going to do it again, you'll see that when x is less than 3 and greater than or equal to 1, f of x looks like x cubed. So this is going to be just the limit as x tends to 3 from the left of x cubed, and that limit is going to be 3 cubed, which is just 27. And let's see about the right hand limit. The right hand limit of f of x as x tends to 3 is equal to the right hand limit of, well, what does f of x look like for x bigger than 3? If we were to go up to the top, we'd see that for x bigger than 3, f of x looks like 2dx plus c. So we get to replace f of x by 2dx plus c here. And when we take the limit of this function as x tends to 3, we just get the value of this function at x equal to 3, which is 2d times 3, 6d, plus c. All right, so going up, we saw that if f was going to be continuous at 3, we would need the left and right hand limits at f to equal 6d plus c. The left hand limit is 27, so we'll need 27 to equal 6d plus c. And what about the right hand limit? We will need the right hand limit to equal 6d plus c, and in fact the right hand limit is actually 6d plus c, so we're getting this one for free. What we need to worry about then is choosing d and c so that this left hand limit, which has to equal 6d plus c for f to be continuous at 3, equals 27, as this is the actual value of that left hand limit. So what we're going to need for f to be continuous at 3 is we're going to need 27 to equal 6d plus c. So let's write that down. All right, so we need this right hand limit, excuse me, we need the right hand limit we got for free. We need this left hand limit, as we said above, to equal 6d plus c, and what the left hand limit actually equals, we need the left hand limit to equal 6d plus c. What it actually equals is 27, so we need 6d plus c, the left hand limit, to equal 27. Okay, so that is we need 6d plus c to equal 27. That's what we need for f to be continuous at 3. Okay, so we now have two conditions. For f to be continuous at 1, we needed, go up here, for f to be continuous at 1, we needed c minus d to equal 1. For f to be continuous at 1, we needed c minus d to equal 1, and if we come down here, we had that for f to be continuous at 3, we needed this condition star star 6d plus c to equal 27. Alright, so all we need then is to satisfy these two equations. Let's switch back to blue, I guess. So we need c and d to satisfy equations star and star. So we need from star and star star the first equation that we wrote down, which was c minus d to equal 1, and c plus 6d to equal 27. Alright, so what we have here are two equations in the unknowns c and d. And we can solve these in a number of ways. If you happen to have taken linear algebra, you'll notice that these are two linear equations and two unknowns. You can use a matrix setup if you want to, but it's not necessary at all and won't be ever in this class. We can just do the following. So let's first solve for, so we're going to solve for C or D, if we like, using one of these equations, and then substitute what we get into the second equation. Looking at this first equation, we could easily solve for C. So this implies that C is equal to D plus 1. And now what we can do is substitute this into our second equation. And if we do that, we'll get that. What is C? C is D plus 1. This is going to give us D plus 1, that's our C, plus 6D is equal to 27. Alright, so C plus 6D is 27, but C is D plus 1, so D plus 1 plus 6D is 27. Rewriting this, we get 7D plus 1 is 27, and subtracting 1 from both sides, we get 7D is 26, and that implies that D is equal to 26 divided by 7, which can't be simplified any further than that. Now, what are we going to do? Well, D is 26 over 7. To find C, we just substitute back into this formula here. C is therefore equal to D plus 1, which is 26 sevenths, plus 1, which is equal to 26 plus 7, which is 33 over 7. All right, and that does it for f to be continuous at 1 and 3, and therefore everywhere we needed these two equations to be satisfied, and these are satisfied when C equals 33 sevenths and D equals 26 sevenths. So, last line, here's our last line. So, hence, f is continuous at x equal to 1 and x equal to 3, and therefore everywhere, remember we got continuity everywhere else for free, when, in fact exactly when, C is equal to 33 divided by 7, 33 sevenths then, and D is equal to 26 sevenths. And that finishes this example.